So we're going to cover section 7.2 and 7.3 here in the same video since they discuss some common things. So remember, the population is all of everyone that we're trying to survey, or everyone that we're interested in, or everything that we're interested in. So again, we can't really usually ask the entire population. We can't send them a survey. We can't collect all of that data. So while the population is described by what we call parameters, those parameters are largely unknown to us. We can't possibly know all of that data usually. So instead we sample, and therefore we use statistics to describe the sample. So we've talked in the first video about some ways to do sampling better, to make better samples, but the statistics that we use them to draw conclusions and make inferences about the population parameters. So obviously they're not exact. We're never going to get the exact mean of the population or the exact standard deviation of the population, but we use the sample to estimate and to draw conclusions about the population as a whole. So an estimator is the statistic that we use to estimate the population parameter. So for example, we use X bar, which is the mean of the sample, to estimate mu, which is the mean of the population. Now, we may draw lots of samples, which means we may have lots of X bars. And for every sample that we draw, we're going to have a different mean. So let's say that we are collecting data and we draw 10 different samples. That means we have 10 different means. Well, which one is the true mean of the population? Well, the answer is all and none. Chances are none of them are the exact mean of the population, but we can look at all of the means of all of the samples and draw conclusions and draw estimates about what the mean of the population is. So again, every time we draw a sample, we have a new mean. We have a new population, new X bar, a new sample mean, and then all of those sample means together we'll use to estimate what mu is, the mean of the actual population. Now, when we call the sampling distribution of the mean, that means if we were to graph all of the sample means, that would give us that sampling distribution of the mean. So chances are, if we've drawn good samples, all of our sample means will be close, they'll be similar, they won't be exactly the same, but they'll be close, assuming that we've used good sampling techniques. So we can say that the expected value of X, or the expectation of X, is mu, and therefore the expected value of the sample mean is X bar, which is the mean. Now, the central limit theorem is an interesting concept that really has a lot of application for us in statistics. What the central limit theorem tells us is that for any population, even if the population itself is not normally distributed, if the sample size is sufficiently large, which as a general guideline means more than 30, but certainly that's not a hard and fast rule, but but if the sample size is sufficiently large, then we can take all of our samples, our sample means, and the distribution of those sample means will be normally distributed, which means it falls under that bell curve, which means that we can use a lot of these normal statistics that we're learning and will continue learning, even if the population itself is not normally distributed. So that's a real game changer for us, because the population a lot of times may not be normally distributed, or we may not know if it's normally distributed. But if we take enough sufficiently large samples, then we can use those means to estimate, to calculate. Basically, we create a bell curve of the means, and we can apply statistics to that, normal statistical principles, because those means are normally distributed. And we're going to see a picture of that here on an upcoming slide. So here we can see 3 samples. We have a sample size of 1. That's the blue kind of box that's just drawn. That's what we call a uniform distribution. We have a sample size of 5. Now that looks fairly normally distributed, but then we have a sample size of 30, and here we have this nice bell curve. Now let's look at a different example. Here we can see again the blue bar is the sample size of 1. Well, that's clearly not normally distributed. Now look at the green line. The green line is a sample size of 5. Again, this is right skewed, so not normally distributed. But even when that is not normally distributed, if we draw a sample size of 30, then now we see that normal, we start to get more of that bell curve. So again, then we can, as long as our sample sizes are sufficiently large, we can apply these normal statistics to them. Now, the same concepts apply when we're talking about the sample proportions. So a lot of times we want to know what proportion of people and things like that. So our sample proportion is P bar, and we use that to estimate the population parameter or the population proportion. So the expected value of P bar is just the population proportion, and then we can calculate the standard deviation of P bar as, and you see that formula, P times 1 minus P divided by N, and then take the square root of the whole thing. Now, for the central limit theorem does apply to the sample proportion. However, it's a little bit different. We can't just say, oh, you have to have a sample size larger than 30. So as a general guideline, the normal distribution with respect to proportions is approximated when N times P, so N is the sample size multiplied by the population proportion, is greater than 5, and N times 1 minus P is also greater than or equal to 5. So what this means is we sometimes might need larger sample sizes, especially as the proportions that we're seeking get farther and farther away from 0.5. So the larger or the smaller, the more extreme, the more that we're looking for the edges, we're going to need larger sample sizes for that. And then if P is normal, we can also standardize that, and that formula for the mean was also on a previous slide. I didn't really go into it, but we have that formula there that if we need to standardize it, we can. So again, here we're looking at some sampling distributions of the proportion, and we see if N is equal to 20, that's the blue line there. Well, that's not a normal distribution, right? That is right skewed. But as we get closer to N of 100, it's still a little bit skewed, but notice it's much more normal, much more bell curve than the smaller sample size. So this is in particular is looking when the population proportion is 0.1 or 10%. And here we see if we're looking for a population proportion of 0.3 or 30%, so closer to that 0.5. Remember, the closer you get to 0.5, the smaller the sample size you can have and get by with. Here we see 20 is more normally distributed, and 100 is definitely more normally distributed.